Hi there. Now in this video what I want to do is show you how we can differentiate y equals the inverse tan of x over a, or some people call it arctan x over a being a constant. Not only are we going to look at differentiating this, but also we can derive a standard integral from the differential. So when it comes to differentiating this, there's two ways that we can do it. Both though require us to take the tan of both sides. So if we do that, we've therefore got the tan of y equals x divided by a. Now what we could do is we could make x the subject, and this will be one of the ways that we'll do it. If we make x the subject, x would equal a times the tan of the angle y. Then we could differentiate this with respect to y, or we could differentiate this from this stage implicitly if we differentiate with respect to x. I'll do this way first though. Okay, so if we were to differentiate this with respect to y, we would therefore have dx by dy, okay, equals a, the constant a, times the differential of tan y with respect to y, which would be sec squared y. If we opt to differentiate this implicitly, then we would need to just put here differentiate with respect to x, and if we do that, differentiating tan y with respect to y first of all would therefore give us sec squared y, and then we need to multiply that with dy by dx. And then if we differentiate x over a with respect to x, since a is a constant, what we get left with is just 1 over a. Now both of these versions have sec squared y in them, and we need to express that in terms of x. And to do that, we turn to an identity that you should be familiar with, and that is that sec squared of an angle, let's say y, is equal to 1 plus tan squared of that same angle, y. And we know that tan of y is equal to x divided by a. So this is going to be the same then as 1 plus x squared over a squared. And I can now express this all over one common denominator, and that would be a squared. And if I do that, we've got the denominator here, a squared, and then we're going to have in the numerator a squared plus x squared. And this is a result then that we're going to be using. So I'll just border this off. Okay, so can just use it. Okay, so if I take a squared plus x squared over a squared for sec squared y now, substitute it, say, into this version here, what we're going to have is a squared plus x squared then, all divided by a squared, multiplied with dy by dx, is going to equal the 1 over a. If I use this method here, we're going to have dx by dy equals a times sec squared y, which we see here is a squared plus x squared then, all divided by a squared. I'll put that in brackets there. Now, when we look at both of these versions, you'll notice in this one here, this a cancels with the a squared here. Now in this version, if I multiply both sides by a, then this a will be cancelled out, and then I'll just be left with an a in the denominator here. Now we need dy by dx, and for this version I turn to the result that dy by dx, I've written since dy by dx, this is equal to 1 divided by dx by dy. As I say, you should be familiar with that result. So can you see from this result that if we reciprocate this, then dy by dx is going to equal a all over a squared plus x squared. And we'll get exactly the same result here if I took this one and just divided both sides by a squared plus x squared and multiplied both sides by a. So whichever version that you take here, let's just border that off, we can see that if y equals the inverse tan or arctan of x divided by a, then it follows that dy dx equals a constant a, all divided by a squared plus x squared. So I'll just border that, and you'll generally find this result in your formula book. Okay, so do check that out. Sometimes you will find though that it's just written as y equals the inverse tan of x, where a equals 1. When y equals the inverse tan of x, dy dx will be equal to 1, all divided by 1 plus x squared. So do check that out. Now there's a spin-off of this. We can see that from this result, if we were just to look at the integral of, say, 1 divided by a squared plus x squared, and this was integrated with respect to x, then we know that if it were a all divided by a squared plus x squared, this result here, it must be equal to the inverse tan of x over a. But now I've written the 1 here, this result, if I make the adjustment, will be 1 divided by that constant a times the inverse tan of x over a, plus a constant of integration, of course. So it's important then that you are familiar with this result here as well. And again, you're likely to see this in your formula book, but nonetheless I'd encourage you to try and remember that one. So hope that's given you some idea then on how we go about differentiating arctan or inverse tan of x over a. We get this result, and then the consequence of that is that we've got this integral here.